Every time you charge your phone overnight, you're relying on a piece of chemistry that hasn't fundamentally changed in over 30 years. Lithium ions sloshing through a liquid electrolyte back and forth thousands of times until the chemistry finally gives out. It's the same basic principle whether you're charging a laptop, an electric toothbrush, or a 2-ton electric car in your driveway. And for cars specifically, the scale is staggering. If you lined up every lithium-ion battery pack installed in electric vehicles worldwide last year, end to end, the line would stretch for thousands of kilometers, farther than driving from Beijing to Berlin. That liquid electrolyte inside each one of those packs is a compromise engineers have lived with since the technology was commercialized in 1991. It works. It's gotten us this far. But it has a ceiling, and the entire EV industry has been quietly bumping against that ceiling for the better part of a decade. But here's the part most people never hear about. That liquid electrolyte is flammable. It's the reason electric vehicle fires, while statistically rarer than gasoline fires, tend to burn hotter and are harder to extinguish once a battery goes into thermal runaway. It's also the reason energy density has plateaued. You can only pack so much liquid-soaked material into a battery before you run out of room to also fit in more energy-storing material. For years, this has been the quiet ceiling above the entire EV industry, one that no amount of software or design cleverness could get around. Now, a Chinese company most people know for building cars is trying to remove that ceiling entirely. On February 9th, 2026, BYD's Investor Relations Department confirmed the company is on track to begin small batch production of an all-solid-state battery in 2027, one that replaces the liquid electrolyte with a solid material altogether. If you enjoy videos about the unglamorous engineering breakthroughs quietly reshaping how the world moves, hit like and subscribe so you never miss one. Why didn't anyone fix this sooner? The honest answer is that liquid electrolytes were never a mistake. They were a genuinely good trade-off for the technology available in the early 1990s. Liquid electrolytes are cheap to manufacture, they flow easily into a cell during production, and they make good contact with electrode surfaces without needing extreme pressure or heat. Solid electrolytes, by comparison, are stubborn. A solid material doesn't naturally want to touch another solid material perfectly, and any tiny gap between the solid electrolyte and the electrode creates resistance, which kills performance. Researchers have known about solid-state battery chemistry since at least the 1970s. BYD itself started internal research into solid-state lithium batteries before 2016, according to industry reporting. So this is not a sudden idea. It's a problem that has quietly resisted a full decade of serious, well-funded attempts by nearly every major battery maker on Earth. Toyota alone has reportedly invested more than $15 billion into solid-state battery development and holds more patents in the space than any other company. And even Toyota has pushed its production timeline back multiple times. The obstacle was never ambition. It was a genuinely hard materials science problem. How do you get two solids to behave like a liquid and a solid do together without losing the safety benefit that made you want a solid in the first place? Dendrites were the other stubborn issue, tiny needle-like lithium structures that can grow through a solid electrolyte during charging and eventually pierce all the way through, causing a short circuit. Solve the interface problem without solving dendrite growth, and you've built an expensive battery that fails early. Solve dendrite growth without solving the interface problem, and you've built a safe battery that barely holds a charge. For most of the last 15 years, every lab in the world has been stuck solving one problem at a time. And there's a subtlety here that most coverage skips entirely. Announcing a 2027 timeline doesn't mean a finished showroom-ready battery in 2027. Industry analysts distinguish between what's called TRL7 or TRL8, meaning prototype testing and real-world system verification, and TRL9, which is full commercial deployment at scale. Most of the 2027 dates you'll hear from BYD, Toyota, and Chery actually refer to that earlier TRL7-8 stage, not the moment these batteries show up in ordinary dealership inventory. That distinction is exactly why BYD's own chief scientist, Lian Yubo, has been careful in public statements not to overpromise. The chemistry that changed everything. BYD's approach centers on what's called a sulfide composite electrolyte, paired with a high nickel cathode and a silicon-based anode. Sulfide electrolytes conduct lithium ions almost as well as liquids do, which was historically one of the biggest arguments against going solid at all. According to Sun Huajun, Chief Technology Officer of BYD's battery business, Shenzhen BYD Lithium Battery Co., sulfide electrolytes are longer lasting and more stable than the liquid lithium-ion chemistry used today, and they enable meaningfully faster charging. Think of a liquid electrolyte as sand poured loosely into a jar. Ions can move through the gaps easily, but the whole structure is unstable and flammable. A solid sulfide electrolyte is closer to compressed stone, dense, stable, and far harder to ignite, but only if you can force the ions to move through it just as efficiently as they moved through the sand. That's the specific problem BYD says it has now cracked well enough to commercialize. The disclosed specifications describe a battery cell capable of an energy density of up to 400 watt-hours per kilogram. For comparison, BYD's current Blade battery, an LFP battery already considered efficient by industry standards, sits at roughly 150 to 190 watt-hours per kilogram. That means BYD's solid-state cell is targeting more than double the energy stored per kilogram of battery weight in the same footprint. In practical terms, that specification is expected to support a driving range exceeding 1,000 kilometers on a single charge, along with the ability to charge from roughly 0 to 80% in about 10 minutes, and a cycle life of up to 10,000 charges. For a commercial EV battery, 10,000 cycles is an enormous number. Most liquid lithium-ion packs today are rated for somewhere between 1,000 and 3,000 full cycles before meaningful degradation sets in. BYD has already applied for multiple patents covering the electrolyte itself, the electrode preparation process, and the battery pack architecture, which is typically a signal that a technology has moved past pure laboratory curiosity and into something a company intends to actually build at scale. The company's development history backs that up. In 2022, BYD completed a 10 amp-hour solid-state prototype cell with an energy density of 280 watt-hours per kilogram. By 2024, a 60 amp-hour all-solid-state pilot unit had rolled off a trial production line at BYD's Bishan base in Chongqing. That's the trajectory. Prototype, pilot line, and now a confirmed 2027 small batch production target, each step verified independently by Chinese industry media, rather than announced once and left unconfirmed. It's also worth being precise about what solved means here. In April 2026, Lian Yubo, BYD's chief scientist, said publicly that the company's solid-state battery program had entered what he called a critical breakthrough stage, while stressing that commercialization still faces real constraints around engineering complexity, cost control, and production yield. He specifically named solid-solid interfacial stability and lithium dendrite suppression as the two core technical bottlenecks still being worked through, the same two problems that stalled the entire industry for the past decade. That's not the language of a company overselling a press release. It's the language of engineers who know exactly which two problems are left and are telling you so directly. The government-backed alliance nobody saw coming. BYD isn't chasing this alone, and that detail matters more than it might first appear. According to Reuters reporting, the Chinese government committed roughly $830 million to finance a collaboration between 6 of the country's leading battery and automobile manufacturers, specifically to accelerate solid-state battery deployment. The companies named in that initiative are CATL, Weilian, BYD, FAW, Geely, and SAIC Motor, a lineup that spans nearly the entire Chinese EV supply chain from battery cells to finished vehicles. CATL, the world's largest battery manufacturer, is separately advancing its own sulfide-based solid-state batteries, with prototypes already reported at 500 watt-hours per kilogram, and a dedicated research team of more than 1,000 engineers working the problem in parallel with BYD's team. That's not a coincidence, and it's not just competition, it's a coordinated national push to make sure that whichever Chinese company crosses the finish line first, the underlying manufacturing base and patent portfolio stay inside the country. Other Chinese automakers are moving just as fast, and in some cases faster on paper. Changan Automobile has said its solid-state battery reached an energy density of 400 watt-hours per kilogram with a CLTC driving range over 2,500 kilometers, and claims a 70% improvement in safety using AI-powered diagnostics during production. Chery revealed its own all-solid-state battery roughly a month after Chang'an's announcement, also citing 400 watt-hours per kilogram and a range beyond 1,500 kilometers, intended for its Exceed Lifeng and Exceed ES8 models. SAIC Motor, working with a partner called Qingtao Energy, has already produced a prototype vehicle using what it calls a Guangxi all-solid-state battery, building on the semi-solid MG4 it launched the year prior, which it marketed as the world's first mass-produced semi-solid-state electric vehicle. Even smaller Chinese battery makers are in the mix. Calb, a battery manufacturer far less known outside China, presented a 60 amp-hour all-solid-state prototype in March 2026, with an energy density exceeding 450 watt-hours per kilogram, ahead of BYD's own disclosed figure. So the picture emerging isn't one lonely lab making a single breakthrough. It's an entire national industry converging on the same chemistry from several independent directions within months of each other. The world starts paying very close attention. When one country's automakers all converge on similar numbers around the same year, competitors elsewhere don't get to look away, and they haven't. Toyota, which holds more solid-state battery patents than any company on the planet, has partnered with Sumitomo Metal Mining, specifically to secure cathode materials for its own solid-state push, aiming for mass production in 2027 or 2028. Samsung SDI completed what was, at the time, the world's largest solid-state battery pilot production line back in 2023, and has since partnered with BMW and Colorado-based Solid Power to validate sulfide-based cells in a modified BMW i7 sedan being tested on roads in Munich. QuantumScape, based in California and backed by Volkswagen, has taken a different technical route entirely, an anode-free lithium metal design using a ceramic separator, and has reported energy densities above 800 watt-hours per liter in 2025 testing, though independent scaling to full production remains unproven. Honda is running its own pilot plant in Sakura, Japan, targeting both automotive and aerospace applications, while Nissan already has a pilot production line running at its Yokohama plant, aiming for commercial vehicles by 2029. One battery industry executive, speaking about the broader race to ePower.com, described it plainly. Companies pursuing different chemistries and strategies are all converging on roughly the same production window, which itself is a signal that the underlying science has finally caught up to the ambition. None of these companies are copying BYD's exact chemistry, but every one of them is racing toward the same destination BYD has now put a hard date on. And that convergence, more than any single company's press release, is what tells you the technology is real. The proof point nobody can wave away is the timeline discipline itself. Unlike a one-off lab demonstration, BYD's roadmap has now been confirmed twice through independent reporting from Chinese financial media, first through Sun Huajin's remarks at the second annual China All-Solid-State Battery and Development Summit, and again through BYD's own investor relations department in February 2026. The company's stated plan is to deploy the technology first in a demonstration fleet of roughly 1,000 vehicles under its premium Yangwang brand in 2027, a controlled, monitored rollout rather than a mass consumer launch. From there, BYD's own roadmap targets what it calls solid-liquid parity by 2030, meaning cost and performance on par with today's liquid batteries, with deployment scaling toward an estimated 40,000 vehicles by that point. Industry analysts at Shanghai Metals Market project all solid-state battery shipments across the whole Chinese industry could reach 13.5 gigawatt-hours by 2028, alongside a much larger 160 gigawatt-hour market for semi-solid designs used as a bridge technology in the meantime. That's the difference between a demo and a real industrial plan. Specific vehicle counts, specific years, and a specific cost curve that BYD has committed to in front of investors, not just in front of cameras. The safety case has receipts too, and they're more nuanced than a simple "solid is safer" headline. Researchers from Newcastle University, working with Poland's Fire Service Academy, ran a comprehensive comparison of lithium-ion, sodium-ion, and solid-state battery chemistries under real failure conditions. Their findings showed solid-state batteries, particularly oxide-based versions, reaching thermal runaway propagation rates of roughly 0.3 to 0.9 degrees Celsius per minute, compared to 9 to 11 degrees Celsius per minute for high-nickel liquid cells, a dramatically slower spread if something does go wrong. But the same research flagged that sulfide-based solid electrolytes, the exact chemistry BYD is using, carry their own documented risk. They can release hydrogen sulfide gas if the cell casing is breached and moisture gets in. That's not a hidden flaw BYD is covering up. It's a known measured trade-off that patent filings on sulfide battery sealants, including designs using particulate fatty acid silver additives, are specifically engineered to suppress. In other words, the industry isn't claiming sulfide solid-state batteries have zero risk. It's claiming, with published lab data behind it, that the specific risks are different, smaller in most failure scenarios, and increasingly well understood at the engineering level. How big could this actually get? If solid-state batteries reach cost parity with liquid batteries by 2030, as BYD's own roadmap projects, the impact wouldn't stay contained to premium vehicles. Doubling energy density at the same weight and volume means either dramatically longer range for the same size battery, or a dramatically smaller, lighter, cheaper battery for the same range. And manufacturers will likely split the difference depending on the vehicle class. Removing the flammable liquid electrolyte also removes one of the last major objections skeptical buyers raise about EV safety, which matters more for mass adoption than most single-spec improvement ever could. And because BYD builds both the batteries and the cars, unlike competitors who have to sell cells to outside automakers, a real breakthrough here could move from patent to production line faster than anywhere else in the industry. None of this means the technology arrives on schedule or arrives evenly. That moisture sensitivity issue in sulfide electrolytes isn't just a lab curiosity. It's part of why Toyota's own sulfide-based program, despite billions in investment, has pushed its production timeline back multiple times because a manufacturing floor solution has to work at gigawatt-hour scale every single day, not just once in a controlled lab environment. Scaling from a 60 amp-hour pilot line to true gigawatt-hour mass manufacturing is a jump that has stalled other battery technologies before, and BYD's own 2027 target is explicitly for small batch production. not mainstream availability. Cost is the other honest barrier. Industry estimates cited by Shanghai Metals Market suggest solid-state batteries need roughly a 15 to 20-fold cost reduction by 2027 just to approach competitiveness, with true price parity with liquid batteries not expected until 2030 at the earliest. That gap means the first vehicles carrying this technology will likely be limited, premium priced, and geographically concentrated in China before the rest of the world sees meaningful availability. Developing markets, and even many developed ones outside China, Japan, Korea, and parts of Europe, may not see solid-state EVs on ordinary dealer lots until well into the 2030s, long after the wealthiest buyers in the wealthiest cities already have them. None of that undercuts the underlying science. It just means the distance between what's technically possible in a lab in Chongqing and what's sitting in an ordinary driveway anywhere in the world is still measured in years, not months. Which brings us back to that liquid sloshing quietly inside your phone, your laptop, and maybe the car in your driveway right now. It's easy to think of a battery as the boring part of a device, the part nobody designs a product around, the part you only think about when it runs low. But the honest truth is that almost every leap in portable technology over the last 3 decades, from phones to drones to electric cars, was ultimately bottlenecked by exactly this. How much energy could be safely packed into how little space? Solve that problem properly, and you don't just get a better car. You get a preview of what comes next for everything else that runs on a battery. If you found this one interesting, tap like, subscribe, and turn on notifications so you catch the next breakdown of an engineering story most people never see coming. Solid-state batteries have been 5 years away for most of the last 15 years. So here's the real question. When an entire national industry converges on the same production year at the same time, is that a coincidence? Or is that what it actually looks like right before technology finally arrives on schedule?